Errors in past studies could undermine conservation plans. F1 on F for the sand tiger shark Carcharius taurus can live up to twice as long as was once thought. Many sharks are living much longer than was thought, according to a major review of studies on these important and often endangered top predators. This means that many estimates of how threatened particular species are, and decisions about whether they can be fished safely, could be based on faulty data. Scientists usually estimate how old sharks are by slicing through their spines and counting distinctive pairs of bands seen inside, which are often assumed to show age in the same way as the rings of a tree. But a growing number of cases are suggesting that the method can be problematic. For example, a 2014 STUDY2 showed that sand tiger sharks Carcharius taurus, which were thought to live for around 2 decades, can actually survive for up to twice that. And in 2007, researchers found that New Zealand porbeagle sharks lamniasis had been underaged by an average of 22 years. To investigate the scale of the problem, fisheries researcher Alastair Harry of James Cook University in Townsville, Australia, reviewed evidence for age underestimation. He reports in Fish and FISHERIES1 that of 53 populations of sharks and rays for which there are good data, 30% have probably had their ages underestimated. See graphic. Current evidence points to it being systemic rather than restricted to a few isolated cases, says Harry. We really can't ignore it anymore. Sharks aren't trees. Growth rings are used to determine age in fish of all kinds. In teleosts, a group that contains the majority of bony fish, researchers tend to look at otoliths, lumps of calcium carbonate in the inner ear, that build up layers regularly throughout the fish's life. But sharks and rays don't have otoliths, so researchers often use sections of vertebrae instead. Sometimes, when sharks stop growing, so do their vertebrae, which means that counting the rings can make an animal seem younger than it is. Harry's paper looked at 2 methods of checking whether the age estimated from counting rings is correct: chemical marking and BIM carbon dating. In the former, researchers capture an animal and inject it with fluorescent dye that is taken up by its spine, making a permanent mark. When the animal is recaptured later, it is possible to count how many bands have formed since this known date. In the second method, scientists can look for carbon traces of 1950s nuclear bomb tests in animals that were alive then, and use this to estimate age. Harry has done a very nice job, says shark scientist Stephen Campana of the University of Iceland in Reykjavik, who has worked on more than 100 aging studies in sharks and rays, as well as in bony fish. I fully agree with his conclusions that shark age underestimation problem is indeed a big one. Management headache. The study has wide-ranging implications, says Lisa Natanson, a fisheries biologist with the U.S. National Oceanic and Atmospheric Administration in Narragansett, Rhode Island, who was one of the paper's reviewers. If age information is wrong, models that guide fisheries decisions about how many animals can safely be caught will also be wrong. Key processes such as growth, mortality, and reproduction changed with age, although precisely what this means for conservation will vary with each species. On the one hand, if living longer means that an animal matures and starts reproducing later in life, underestimating age will mean that it is more vulnerable than has been realized. On the other, living longer might give animals more breeding years, making a population more robust. Emerging technologies could help to solve the aging problem. Methods include looking at aspartic acid, an amino acid that is produced in living organisms in one of 2 forms, then slowly converts to the other in inert tissues through a process called racemization. Near-infrared spectroscopy could be useful too, says Natanson. Complete reliance on backbones has got to disappear. Journal name Nature Volume 549, pages 316-317. Date published 21 September 2017. doi 10.1038 Nature.2017.22626 Harry, A.V. Fish http://doi.org 10.111 15.1224 2017. Passarati, M.S. et al. Mar. Freshwater Res. 65, 674 687 2014. Francis, M.P., Campana, S.E. Jones, C.M. Mar. Freshwater Res. 58, 1023 2007. For the best commenting experience, please log in or register as a user and agree to our community guidelines. You will be redirected back to this page, where you will see comments updating in real time and have the ability to recommend comments to other users. Comments: there are currently no comments.